let's get started. Really, it's open. I did do your test. I have actually written your final. So I can tell you right now, it's got 10 questions in it, and there are chronological order, and there are no multiple choices.
Can we see it?
Yes, on Monday. I will let you see it then, but not until then, for pretty obvious reasons. So the last thing you're going to be seeing is triple integrals using cylindrical coordinates. So I'm not really giving much away by saying that if you take the major topics that we've done, you're going to get a question on it. So triple integrals using cylindrical coordinates, triple integrals in general, double integrals, Lagrange multipliers for finding max and min, you know, all the major stuff. You're going to get a question on each of those. So most questions are going to be one question per topic. So I'm not going to give you 2 questions on anything. So you won't get 2 questions on finding the volume of an object or something. It would be a triple integral question, and that would be it. It would either be that or a different version of it. Okay, any questions? Let's get started. Give me a topic to go over or whatever.
Yeah, I was having some trouble on number 1 on surface area part B. I know you went over it, but I was just having some issues.
That question's been driving me crazy with. You're not the only person who's had issues with that question.
I have some comments on that question.
Yes, but they're probably not polite ones or they're anything like me.
Yeah, I had trouble and I found it in the book and then went to the back, and how they did it is just plain weird at the end.
Well, that's probably no use to me. Plain weird at the end is not good. It's going to take us a while, but I can certainly do it. You want me to do it?
Yes, please.
Okay, here goes. The version I've got, well, at least the version I've got's got the answer on it. So why don't I look at their solution? But sometimes they do it weird as well. Okay, they've got an answer. Right. So when I'm finished, the answer better be pi minus 2 a squareds. So we have an x squared plus a y squared plus a z squared equals a squared. And we have an x squared plus a y squared equals ax. And we're being asked to find the area of the surface of the part of the sphere, that's this guy, that lies within the cylinder, which is this guy. Okay. So the Z guy that we're going to be dealing with comes from here. So if I rearrange this guy, let's do it down here. If I rearrange this guy, can I cut a lot of corners here for speed purposes? But are you okay with that being Z if you rearrange it? Right. Subtracting x squared, subtracting y squared, and then taking the square root of everything. Are you comfortable with that? Right. So I'm just doing the building framework here. So that's essentially our f of xy. So if I do a partial derivative of this with respect to x, I'm going to have to do that version of the guy. And so his derivative is 1/2 a squared take away x squared take away y squared to the -1/2 power times the derivative of the inside function, which is -2x. And when you tidy that up, you get -x over a squared minus x squared minus y squared to the -1/2. Are you comfortable with the partial derivative of this with respect to x? And that's a +1/2, by the way.
Yeah, because our a squared minus x squared minus y squared is in the, oh yeah, positive 1/2. Never mind.
Right, okay. So what I'm going to do, I might as well do it here then, is can't I just square that? Because that's what you're going to do inside the square root. And if you square that, you get actually something a little bit nicer to deal with. You get that. You're comfortable with squaring top and bottom. And by symmetry, are you okay with me just saying that that's what the other guy's going to be? Right. So far, so good. So what we're going to deal with is the triple integral guy, the square root of this guy squared plus this guy squared plus 1. And why am I doing the triple integral? It's a double integral, right? And we've got our guy. This fella here is going to be him. So that's x squared over a squared, take away x squared, take away y squared. And then the guy next door is going to look like this. And I've got, what, a plus 1. Are we good? I'm not going to worry about the region D yet. Let's just keep him out the picture for the time being, because he's really want to focus on just making this pretty. You can add these two together because they share a common denominator. You got a plus 1. I want to get these together, so what I'm going to essentially do is take this fella and add 1 to it, but the version of 1 I'm going to use is the one that has that common denominator. And if you now add these fractions together, you end up with just an a squared on the top and this guy on the bottom. Are we still good? I know I'm zooming through this, but are you following the steps? Okay, so what we're going to now do is keep the theme going. Separate that out, you get an A, and on the bottom, you get that. But I'm going to be using polar coordinates, and I know that because something else that's coming up. So since I'm using polar coordinates, minus x squared minus y squared becomes minus r squared. And since I'm using polar coordinates, it's going to be an r, dr, and d theta. Are you comfortable about converting to polar, in which case that becomes an r squared as well? Now, the only thing that we don't have yet is the region D. And the region D was described as being this guy. So I want polar, and I'm certainly going to get polar from this. Won't this be r squared? And won't x be r cos theta? And that makes r equal to a cos theta. And no, I didn't take the square root of both sides. What I did is I divided both sides by r, making the assumption that r isn't 0. If you put that guy in, now I don't remember what that thing looked like. It was a circle. It was a circle centered at A, wasn't it? Did it go? What would nothing get me? Centered here. I may want to check that because there's 2 possibilities, but I think that's the right one. So it ends up being a circle that looks like that, right? Now we have an extra piece of information, and this is, it says it's above the XY plane, which is basically just saying it's above this way, but why am I not being able to use the bottom? Why can I not use the bottom? Oh, I can. If I do projection lines coming out of this guy, it's going to go from that direction to that direction. So that tells me that theta is going to go from negative pi upon 2 to pi upon 2. So if I'm drawing this shape, down there is negative pi upon 2, and then rotate up to there is positive pi upon 2. And the r values are going to go from 0 to a cos theta. Okay, I've got my integral set up. So theta equals, I think I now know where that missing 2 came from, Maggie. Because you had an issue with that same question. We have an a over the square root of a squared minus r squared. R is going to go from 0 to a cos theta. A over that guy times an r times a dr times a d theta. Are you comfortable about the r going from 0 to there? Less obvious. If you draw that thing in Desmos, it's a circle that looks like this, and it goes starting pointing down the way and going up. Now you might think, well, why don't I call this 3 upon 2 pi and this pi upon 2? Well, if you do rewrite it in that order, I think you're getting the thing back to front. I think you're generating this guy and you're going to there. So you're generating this side. So that's my argument anyway for why it's the note. So we have this fella to deal with. Let's just do him on his own. R equals 0 to a cos theta. And AR over the square root of a squared take away r squared dr, right? I'm forgetting about the d thetas right now. We're just going to do that. Would you agree this is going to be a u sub? So differentiating with respect to r gets me that. Doing the crossover gets me that. And then isolating the dr. So we're going to have an integral of AR square root of u times -1 over 2r du. The r's cancel, and there's a negative floating about there. So I'm now looking at negative a over 2, 1 over the square root of u du, which I should have thought about it. I should have called it -1/2. Now you add 1 to the power, and you divide by the new power. You then turn it back into a square root, which you then turn back into that guy. So our integral, which is this one, is going to be negative a, the square root of a squared take away r squared, evaluated at 0 and evaluated at e cosine theta. So it's going to be negative a, the square root of a squared take away a squared cos squared theta, minus, plug in 0 here, you get a negative a, the square root of a squared, which is a times a is a squared, and then you add it. This guy here has a little bit of work you can do to it. If you pull out an a squared, you get 1 minus cos squared. One minus cos squared can be replaced by sine squared. That gets you an a, that gets you a sine a, so you have minus a squared sine theta plus a squared. And so we have done the first integral. And then if I return to the question, we still have to do theta equals negative pi upon 2 to theta equals pi upon 2 d theta. Okay, I'm going to pull out a squared and just do a negative pi upon 2 to pi upon 2 of 1 takeaway sine theta. So 1 takeaway sine theta. Much easier to do. The squares aren't in the road. That's going to be a theta. What happens when you integrate getting a little distracted. Yeah, what happens when you integrate a sine theta?
Well, the sine theta itself becomes negative, and because it's already negative, it becomes positive
Right.
cosine.
And we're going to evaluate that from negative pi upon 2 to positive pi upon 2, and then remember there's an a squared out there. And what have we got then? We have a theta, so that's pi upon 2 plus the cosine of pi upon 2. Take away negative pi upon 2 plus the cosine of negative pi upon 2. Something's not right here. So darn close to the right answer because I can see what is going to come out of this any minute now. And I'm missing a 2. But here, anyway, I want that to be a 1. That would be so much nicer, or even a negative 1, but it's a 0.
Should I tell you what weird thing they did?
What?
They decided to double the thing and get rid of the negative pi over 2 and change it to a 0.
Oh.
And that's what I don't get, how they get
Oh,
away with
that I can get away with. Remember the shape was that guy, right? That was the shape of the area, right? Isn't this top half the same size as the bottom half? So they said, if I find this guy and double it, it's the same as finding the whole thing. So that's the argument behind it. So I'm going to use their argument because I like it and put a 0 there and put a 0 there. And that gets me a 1. And then I can double it. Right. Have you ever done a question where if you knew the shape was symmetric, that you only found this bit because you knew that was the same size, so you only found the integral from 0 to pi and doubled it? You know, you could do something like that. Your thumbs up. You like that? Is that a question, Matthew, or a thumbs up for it works out good?
And that was a thumbs up.
Oh, great. Okay. So, okay. Now that I've got the guy that I wanted, we call it good. And now we have lost the darn thing. That's a 0. And that's actually the one that we need. And so what do we get? We get 2a squared pi upon 2, take away 1, that when you double it, you get a squared pi minus 2, which is the answer. So they decided to not do negative pi upon 2 to pi upon 2. They decided only to do half the shape. So that's 0 to pi upon 2 and then double it because, you know, half a circle doubled gets you a full circle. I would never have thought of that. And yes, it is weird. And I think the only reason that it worked is that some other person figured out that if you did it the way I did it, it didn't get you the right answer. So they had to figure out why. And they figured out that I suppose that using this bottom half in some way interferes with the math, so it doesn't come out correctly. God, that was annoying. But at least I got the answer. And we've already used up half today. So one question. God, that's a good question. No, you can't get this question in your test because it's too blinking big. But you will get a surface area question, just not that one. Okay, apart from the little hiccup at the end where you had to go from 0 to pi upon 2 and double it, instead of from minus pi upon 2 to pi upon 2, everything's cool. So what is our next topic or next question?
For this chapter, whenever we got something like z is equal to the square root of something, how do we know when we're supposed to use the plus or minus of the square root, or have z be equal to 0 and then use the plus part of the square root?
Almost always the shapes tend to be above the plane, so that's not a good answer to say it's always plus because of that, but that's the main reason.
So if the shape ever goes into the negative,
then you do the
z,
negative.
Okay.
You probably have to put it into GeoGebra and look at it to be able to tell. Because if you just see an equation, it's very hard for anyone to tell what does that look like in relation to the XY plane. I mean, is it above it or is it below it? It's quite hard to tell.
Yeah,
so
that makes sense.
if you weren't sure, you put it into GeoGebra. You know, if you get it wrong, doesn't it just typically make your answer minus instead of plus?
Oh, yeah. So should all the answers for volumes
Be
typically
positive.
plus? Yeah.
Yeah. And all the answers when you do double integrals that are asking for area should also be plus. So if it's a physical thing like mass, volume, area, that'd be the three that would come to me. Surface area has to be positive because it's a physical thing as well, typically, right?
Okay. Yeah. Thanks.
But remember in a test, if you get the negative, will you just do one more line and make the answer positive? If you know it should be a positive thing, right? If it's just an anybody triple integral, right, just a random kind of triple, those can be plus, minus, or 0. Just like normal Calc 2 integrals can be plus, minus, or 0. Right, but if it's a volume, area, etc., must be positive. Good question. What's next?
Can we do a center of mass question?
No, we can't do a center of mass question. And the reason we can't do one is that I only have 20 minutes and it'll take me longer than 20 minutes to do a center of mass. But what I can do is give you the process, okay?
Sounds great.
Okay, so if you're doing a two-dimensional center of mass, which is typically the ones you'd expect to see, because three-dimensional ones are just massively big, you would have some function, f of xy, right? And you'd have some region D, which, well, who knows what it is, but can we pretend that x is between 0 and 3 and y is between x and 0, right? So whatever it is, you've got your D to work with. So to get the mass, what you're going to have to figure out here, excuse me, is you're going to do the double integral of the region D, which I should have called that rho because it's a density function. I know it's xy, but you know, is it the density function called xy rho instead of just f of xy? So do you get the mass by doing this? And so in my question, it would be from x equals 0 to x equals 3, and then from y equals 0 to y equals x. And the density functions can be all sorts of things. If they're really nice to you, they'll just make it k, won't they? Which is just a fixed value. If they want to make life difficult for you, won't they say it's proportional to the distance to the origin? In which case, you're going to get a guy like that. Right. Or they might just tell you that the density function is x squared y, because it is, right? They just tell you. So let's pretend that they told us it was x squared y. Then I would do, in this case, a dy and a dx. And of course, you get 42 because it's a real nice question and you get a really nice answer. In reality, don't you get square root of 79s and some ugly stuff? Now, you then go on and you find what these guys are called the moments. Right? You get the moment of x and the moment of y. And these are double integrals over the same region. And then you can bring in your function f of xy. And for this guy, it's y times f of xy. And for this guy, it's x times f of xy. And let's just say that this guy is a nice easy x plus y. Then this integral would be the double integral of y times x plus y dA. And this one would be the double integral of x plus y dA. And these would be the limits of integration. And this guy here would be your usual dx dy guy. And you do a whole load of work and eventually you get 20. And this guy ends up being 10. And you'd have some numbers to play with. Also, sometimes, don't you turn things into polar because they're easy to calculate? So if there's a lot of x squared plus y squareds, or if the region D is part of a circle, won't you do the same calculations, but you would just, you might change them into polar form just because they're easier. Now, once you've got that guy, and the mass, you can get x bar and you can get y bar. X bar is this fella over m, and y bar is this fella over m. And so in my case, it would be 10 over 42, which is 5/21, and this one would be 20 over 42, which would be 10/21. So that would be the process. Right? So you can imagine that there's a lot of integration, right? Integration, the density function, and so on and so forth to get the whole picture. And things you can do. If the region D is your friend, can't you sometimes do symmetry? So some symmetries can be that you know that they're equal to each other, which is very common. Some symmetries are that, you know, well, if it was a 3D, if there was a shape, can you imagine this is 3D and there's a shape above this, I could get away with x bar and y bar both being 0 because the axis of symmetry would be directly above the axis. The symmetry would say that the origin would be the axis of symmetry going upwards. So you just got the Cliff version of how to do a centre of mass for a two-dimensional shape. Three-dimensional shapes are like twice as much work on top of that because you have 3 more integrals. You've got another integral instead of 2 to do here. Plus, isn't everything then going to become a triple integral, not a double? So just time-wise, that would be impractical, at least for the midterm. But for a double integral, as long as, you know, you kept things simple, it wouldn't be too bad. Another question? You know, your time is valuable, and I don't want to be here telling you stuff if it's not being useful for you.
So we review Lagrange multipliers.
Oh, okay, yeah. I'm going to have to find one of them because it's not a good idea to just pick one off the top of your head because they never work. There's one of those kind of questions that you kind of need somebody to do one for you. So, okay, I've got one here. Essentially, what Lagrange multipliers allows us to do is it allows us to find the maximum and or minimum value of a function, right? Subject to a constraint. So let's see if we can find Try to find, well, these ones are the puzzle ones, so I guess I could do that one. Right. So this is a question 6 from the part B section. And the function that we're going to find its maximum and minimum value is a polynomial, which a lot of these guys are, mostly because of the practicalness part. And then you've got x squared plus y squared less than or equal to 81, which is your constraint. And the less than or equal to doesn't really matter too much, and because the function that we call the constraint function in this case is essentially x squared plus y squared minus 81. That's the guy you're going to do. So according to Lagrange multiplier, the gradient of f will be equal to lambda times the gradient g. And the gradient of f is the partial derivative with x and with y, and it's going to be lambda, the partial derivative of g with x and g with y. Okay, so far so good. Right, now, little side issue. When I come to do my constraints, I'm going to look at the boundary of the circle, not necessarily all the points inside, because all the points inside will come when I do lambda 0. That'll basically pick everything else that could happen. So once I've taken care of lambda equals 0, the constraint is it has to be this. Right. So back to our question. 2x plus 8 and 2y minus 8, lambda 2x 2y. And so we set up a system of equations, which is this is lambda times 2x, and this guy is lambda times 2y. I'll call these equation 1 and equation 2. And then we do two different tests. The first one is we assume that lambda equals 0. That is equivalent to saying there's no constraints. So if lambda was 0, then equation 1 would end up being that, and equation 2 would end up being that, and they would generate an x of -4 and a y of +4. Are you comfortable with what the solution would be? So they're saying to us, that might be a place that you're interested in looking. Now, if I do my constraint function, which is that guy, isn't -4 squared plus 4 squared less than or equal to -1. So we finally found a question where lambda equals 0 was usable. Right? Can you imagine in a lot of cases, you try it and you get a point and it doesn't work. So now that we've got that, I'll go back to these two equations and I'm going to say 1 and I'm going to divide it by 2, which is typically what you do. So I'm going to have 2x add 8 over 2y take away 8 is going to be 2 lambda x over 2 lambda y. And what I'm going to try and do here is find some connection between x and y that I can plug in here, and that will allow me to solve the puzzle. Right? It'll allow me to find an x, and then after that a y. If I go through this, I'm going to do two things here. So this is going to cancel, and I've got that. And can I now cancel and cancel? So cross multiply says that this has to be equal to that. Are we good? So that makes xy plus 4y has to equal xy minus 4x. You still good? What could I do next?
We can subtract an xy from both sides, and divide both sides by 4.
Haven't I found then, or haven't we found, because you told me what to do, the connection between the x and the y? In this case, isn't y equal to negative x, right? That has to be true in this situation. So you return to your constraint function, and we're only interested in the boundary now, so it's that guy. And we can say x squared plus negative x squared is 81. So that ends up being 2x squared, which is 81, which means x squared is 9 over root 2, which means x is plus or minus 9 over root 2. And when x is positive 9 over root 2, won't y be the negative of that? And when x is negative 9 over root 2, won't the y be the positive of that? So we now have another critical point. We can have that one. We can have that one. And we can have that guy that I can't remember where he is. Remember? Yes.
Where did the original root 2 come from?
81 over 2, take the square root, 9 over root 2.
Okay, thank you, sorry.
Here it is. I was looking for that third one. So we call these guys critical points, don't we? So what I would do next is when I find the value of the function at each of these different places. And I have the answers in front of me here. So this answer is negative 32. And when you use, which one? The minus one. When you use this one, the answer ends up being approximately negative 20.823. And when you do this one, it ends up being approximately 182.823. So when we look at this, then won't the maximum value be this number? And won't the minimum value be that number? So we found the absolute max and min of the original function subject to a constraint. And if you want to know what those are, according to what I have here, this one is 81 plus 72 root 2's. Obviously, that's negative 32. And if you wanted to know what this one is 81 take away 72 root 2's. I think the only reason they turned them into decimal is that it's kind of hard to tell what a big number looks like when it's got square roots in it and adding and subtracting from other things. Let me show you something. One of the reasons I don't like looking at answers, apart from the fact I make mistakes and I should, is this fella here. Are you looking at the solution to that question we just did? Do you notice that up to about there, it looks just like the way I did it? And then look at what happened after that. That is nothing like the way I teach this. You agree? I do not like the way they teach that. But if you go online, you can find out how to do it that way. I like 1 divided by 2 and 1 divided by 3. And why do I like that? Because doesn't that make the darn lambda just go away and we don't need to worry about it anymore? And then we're just trying to make y equal x or x equal something with y, right? Isn't that our goal after that? And that's a lot easier, in my opinion, to do with it. If you try and do it with this particular method, oh God, no. Right, and half the time when I look at their solutions, I'm not doing it the way I want them to do it. So it's a very big distraction of me. The reason I kept this one open was at least so I could tell you, where is it? What the values are. Now, I'm arrogant enough to think my way is better than that way. That doesn't mean I'm right. So if you do want to figure out how they do that, there are videos out there. Just go and look at, a search like using Lagrange multipliers, and I bet you'll find someone that will walk you through the steps involved there. I do not like that method at all. And there's a couple of other techniques that they do that I go with. Give me another one just at the top of my head because I'm ranting on here. Do you know the cover-up method? You remember that? If you go and see how they do it, not using the cover-up method, it is not pretty. Right. If I see the way my brain works is, if there's an efficient way of doing it, shouldn't you do it? If there's a quick way that gets you the answer, I think dividing 1 by 2 is a quick way to do it. It works well. Will there be exceptions where that method won't work? I'm sure. But see the way they do it? I bet you there's more ways where that method doesn't work. Right, so you're going to have to live with that. Okay, I got my little rant over with. I like ranting, it's fun. For 2.5 minutes, have you got a good question? If not, we're going to say last name and bye-bye. Okay. Have a horrible weekend, as I've told everybody, because if you're not having a horrible weekend, you're not studying, right? So you got to have a really good weekend next weekend, but not this one. So Mia, no boyfriends, girlfriends, or any other friends.
My prom's this weekend. It's tomorrow though, so.
Your what's? Your prom?
Prom. Yeah.
Oh, you can't miss a prom.
Yeah.
No,
I'll
you
still
can't miss
study.
that. Yeah,
I'll still study on Sunday, but it's Mother's Day. But I'll figure it out.
God, Mother's Day, and I am a real nasty person. It's Mother's Day this Sunday?
Yep.
I honestly didn't know that, and you're probably going to say, oh, he must know that. This is true, look it up. Mother's Day in Scotland or Britain is not the same day as my sister had her Mother's Day. God, it was like 3 weeks ago.
Oh, well, that's weird.
Right. So that's why I honestly didn't know it was Mother's Day. I couldn't really avoid it, but that's it. I feel bad. Have a nice time with your mum, but then go and study.
Okay.
Right?
Bye.
Bye-bye. Oh, Father's Day, by the way, is the exact same day as America. So go figure.